So for in this example, I have a solution of H2SO4 and I am beginning with 18 molar H2SO4 solution, and I'm supposed to dilute it to generate 250 milliliters of 0.500 molar H2SO4. So realize in this particular case one can utilize the relationship that essentially moles of the solute are going to remain the same before and after the dilution process has taken place. So moles of solute before should be equal to moles of solute after, and essentially what you say is Mi times Vi, I for initial, is equal to Mf times Vf, where F is for final, and you simply plug in the numbers that you have here. So for instance, 0.500 molar, that will be the final molarity. 250 milliliter, that will be the final volume. Mi is going to be the initial molarity, and volume is what you are seeking. The only one thing that I would want to say here is the units of the final volume will dictate what the final units would be. So go ahead, plug in the numbers and see what you get. You can of course at any given point of time click on the answer, and that will lead you to the video where I show you how to go about it. So I'll leave you with that and start discussing what is called as titration. Titration is a technique where essentially our aim is to determine the concentration of a solution. This unknown concentration is what is called as an analyte, and usually it's reacted with a solution of known concentration, which a lot of times is referred to as the standard solution, or sometimes even primary standard. Now, for any compound to exist as a primary standard, of course, there's some prerequisites. This particular compound should be pretty stable. You can't really have something which decomposes or absorbs moisture, for example, because that was bound to change the chemical composition as well as the mass of what the active component is after a given period of time. But you can utilize in a titration, you can utilize an acid-base reaction, you can use up a redox reaction, you can do a precipitation reaction, you name it. But the aim is that you're going to be running a reaction to essentially figure out the concentration of an unknown solution. So here, just as an example, I'm going to get you started, and in lab 2 we are going to use this in lab as well. I'm going to use a general example of HCl, which is an acid, reacts with sodium hydroxide, which is the base, and it gives you NaCl, which is the salt, and in addition to that you get water. So I'm going to just write water as HOH. Now when you read the reaction, you can perhaps see that it is a completely balanced reaction, first of all, and you can, this is a completely balanced reaction, and you can perhaps envision that one equivalent of HCl reacts with one equivalent of NaOH to give you one equivalent of NaCl and one of water. Now, if you were to think about the reaction and you're going from an acid, let's say you took in an Erlenmeyer flask, you took the acid, and from the burette you add sodium hydroxide till the time it is neutral. You can perhaps envision that this is going to remain a different color, and then a pH increase past the 7 is going to show you a different color, provided you use what is called as an indicator. So very often we use indicators which are nothing but organic acids, and it is their property that in an acid pH, acidic pH, they show one specific type of color, and in the basic pH they show something else altogether. So I'm going to give you the example of what is called as phenolphthalein, because that's what you are going to use in the lab as well. Now this one is colorless when it is acidic, colorless in acid, and red in a base. That means at equivalence point, at the end point, it's going to be with a very baby pink color is what it's going to have. So realize if you don't have this indicator, essentially there'll be no way to tell whether the equivalence point has been reached. That means the complete neutralization has taken place or not. So it's a good idea to put the indicator. Of course, you can use what is called as a pH meter that measures the pH, but it is a very expensive tool. It is an expensive, fancy piece of equipment, something you'll learn about in general chemistry too. For now, consider that phenolphthalein is going to be the indicator, which is going to be a rather inexpensive method of monitoring this neutralization reaction. So at any given point of time, since the moles of acid and moles of base are exactly same, one can say very safely that moles of acid times volume of acid should be equal to moles of base times volume of base. And we are able to say that because we can say by stoichiometry that as the neutralization reaction takes place, 1 mole of the proton interacts with 1 mole of OH negative to generate your water molecule. Now, the question here is, let's see if we can apply that. A 25 milliliter sample of vinegar, which is nothing but dilute acetic acid, is titrated to found to react with 95 milliliters of a 0.2 molar NaOH. What is the molarity of the acetic acid solution? So over here we have sodium hydroxide, which is reacting with acetic acid and gives you sodium acetate and water. Now, acetic acid, as you know, is the acid here, and if you wanted to determine the number of moles of acetic acid, you will simply say that molarity of acetic acid, which is the unknown here, so I'm just going to call that MA times volume of acetic acid should be equivalent to molarity of base times volume of base at equivalence point. Now the base here is sodium hydroxide, so the numbers there are going to be 95 milliliters volume VB and MB is 0.2. So let's plug in the numbers. MA is what I'm seeking, and I can say that 0.2 times 95 divided by 25, and let's write these as, let's perhaps write these as the correct significant figure so that we know what numbers we are dealing with. So hopefully you can see that all these three numbers essentially have three significant figures. And now we are going to carry out the calculation for the math for this problem. And on my calculator, I'm getting a value of 0.76 molar as the final answer. So the molarity, the concentration, is going to be 0.76 molar, and you can use this method to determine the concentration of either the acid or the base, whichever we are seeking. All right. Let's talk about what are called as oxidation numbers, sometimes also referred to as oxidation states. Now, oxidation numbers or oxidation states is this charge that all atoms carry regardless of what the overall charge of the species is. In a sense, one can say that oxidation numbers are actually the real charge that is present either in a monoatomic ion or in a polyatomic ion, and you can perhaps envision that these together contribute to the overall charge of the species. So if you're considering something which is elemental in nature, for instance, if you're thinking about elemental sodium, or maybe sulfur as acid, or neon, which is monoatomic, bromine, essentially it is present in the elemental form as nature intended to make it, and so the oxidation number for these is going to come out to be 0. It's taken to be 0 rather. On the other hand, if you are considering a monoatomic ion, then whatever is the charge that you see, the oxidation state or oxidation number is equivalent to that charge. So for instance, sodium plus has an oxidation state of +1, whereas aluminum 3 plus has an oxidation state of +3. So that's the next thing. The problem is, or the point of discussion is, what happens if we have a polyatomic ion, and how exactly does that pan out. Realize that hydrogen in general will always be given a +1 oxidation number. The only time that it will get a -1 or a -1 is if it is bonded to a lithium 1 hydride, a calcium hydride, or if it's an aluminum hydride. So you can consider that as a group 1 or group 2 or group 3. That is the only time. So a real representative metal, and you can consider that hydrogen is going to be -1 in that case. Then H is -1. Otherwise, by default, it is given a number +1. Likewise, if you consider oxygen, usually it takes a value of -1. On the other hand, in case of peroxides, it is considered to be, did I say -1? No. Oxidation has oxygen has an oxidation number of -2. I'm sorry. And in case of peroxides, it actually happens to be a -1. So that's the exception right here. And the final thing, halogens, they usually have an oxidation number of -1, but when they are bonded to oxygen, which is just more reactive and has a greater electronegativity than the halogens, other than fluorine, of course, then chlorine, bromine, and iodine, they can have a positive value also. So in general, halogens and other metals, they would go by the valency, but they could have positive numbers depending on what they are bonded to, especially if they are bonded to oxygen. So for instance, you can see right here, I'm trying to show you the oxidation number of sulfur in H2SO4 or sulfate ion, and the best way to go about it is that you measure up what would sulfate look like. So let's take a, so we have sulfur, which is my unknown, so let's call that X, plus 4 times each oxygen is bringing in a -2 charge, and together this is summing up to a -2 charge. So one can say X minus 8 should be equivalent to -2, or that X is equal to +6. So the charge on sulfur happens to be +6. And you can do that for, any polyatomic ion that you seek. From perchlorate, this slide shows you perchlorate by the same method, having a value of +7. If you have ClO3 negative charge, you can perhaps envision that you would be looking at chlorine, which is X plus 3 times -2, and the total is giving you a -1 charge. That means X minus 6 equals -1, or X is equal to +5, and that's what we have here. Now, the question here is assign oxidation numbers to each atom in the following, and we're given CdS, cadmium sulfide. In this case, sulfur, you have to consider, is group 6, so it needs only 2 electrons to complete the octet. That means sulfur will be a -2. So sulfur is present as a -2, and that means that cadmium is going to be present as a +2. And since these will be monoatomic ions, you can say very safely that those will be the oxidation numbers on these as well. Aluminum likewise is a group 3 element, And hydrogen, while usually has a +1, in this case will be treated as a -1. So aluminum being group 3 is a +3, while hydrogen is a -1 for this case.